Hello everyone. In this video, we are going to discuss about the relative velocity analysis of a 4-bar mechanism. In the question, a 4-bar mechanism is given. You can write down the question. The driving link is the link AB, which is the crank, and you have to find the angular velocity of the connecting rod, that is BC. The crank AB is rotating with a uniform angular velocity, that is 100 rpm. It is not a angular velocity, it is basically 100 rpm. Rpm is the unit for angular speed. So you need to convert angular speed to angular velocity. Okay. Here in the question, we are assuming that the driving link or the crank is rotating in the clockwise direction. So finally, we need to find the angular velocity of the connecting rod BC. Before going into the details of the problem, first we will try to understand the type of motion of each link in the 4-bar mechanism. We know that in a 4-bar mechanism, link AD is the fixed link. Link AB, which is the crank or the driving link, has a rotational motion. Similarly, the link CD, which is the output link, can have a rotational motion or a rocking motion. Anyway, the link CD is going to rotate about D. So the output link CD can be assumed to have a rotational motion. Regarding the motion of BC, we know that the connecting rod will have a combination of rotational and translatory motion. That is, it will have a general planar motion. But for our analysis, that is regarding the relative velocity analysis, it is assumed that link BC rotates about either point B or point C. That is the assumption that we must have for the relative velocity analysis. So like in the previous question, to start with, first we will be drawing the space diagram of the mechanism. So again, I am going to remind that when you draw the space diagram, you have to use the exact dimension. If you are not able to accommodate the whole figure or the whole size of the mechanism in a paper, then you can scale it down. Or if you want to enlarge the size of the drawing, then you can scale it up. That depends upon you. Here, the dimension, the maximum dimension is for the base link, that is the fixed link AD, that is 600 millimeter. So you can take it as 6 centimeter. Okay, 600 millimeter can be approximated as 6 centimeter, and you can draw. Okay, so like in the previous question, you have to draw. For drawing, you keep the paper horizontally, and at the top side of the paper, you draw the space diagram. Here I have drawn the space diagram. When you draw the space diagram, you also have to label the diagram. That is labeling the joints in the mechanism, and also you give the dimensions and also indicate the type of motion or the direction of motion of the driving link or whichever link whose motion is specified. When you draw the space diagram, you must label the diagram. Also, you have to indicate the direction of motion or direction of rotation, whichever is given in the question. Now, we need to start drawing the velocity diagram. To draw the velocity diagram, first we need to consider the driving link. In the question, it is given that the crank AB is rotating at a uniform angular speed. So angular speed is denoted by N. NBA is given as 100 RPM. As you know, to draw the velocity diagram or relative velocity diagram, we need to find the linear velocity. That is, we need to find the linear velocity of B relative to A. And we know that linear velocity of B relative to A is given by R into omega. Here R is nothing but AB into omega AB or BA. Okay, so here, to avoid confusion, I am going to indicate it as velocity of B relative to A is nothing but BA, that is R into omega BA. BA is the length of the link AB and omega BA is the angular velocity of link BA. To find the angular velocity, we will use the angular speed. How will you convert angular speed to angular velocity? That is, we can find angular velocity BA equal to 2 pi into N BA by 60. Okay, 2 pi N by 60. Using this equation, you can convert the angular speed to angular velocity. Once you find the angular velocity, you can substitute in this equation and you can find the velocity of B relative to A. That is the magnitude of relative velocity of B relative to A. That is what I have calculated here. You will get the angular velocity of link AB is 10.47 radians per second. You multiply that with the length of the link AB. The length is given in millimeters, so you must convert to meters by multiplying by 10 raised to minus 3. You will get the relative velocity of B with respect to A as 9.41 meter per second. So what you get here is the magnitude of velocity of B relative to A. Now we need to represent this velocity as a vector. To represent the velocity as a vector, we now have the magnitude. So we now need direction. So what is the direction of velocity of B relative to A? We know that the direction of velocity will be perpendicular to link AB. And since the link AB is rotating in the clockwise direction, that means the direction will be downwards. Okay. the direction of velocity will be perpendicular to link AB and towards right. Okay. So what you do is you draw a line perpendicular to AB towards right. Okay. And then we need to represent it as a vector. To represent the velocity as a vector, we have now found out the magnitude and the direction. Now, to locate or to start drawing the velocity diagram, below the velocity or the space diagram, first we need to locate the fixed point of the mechanism. We know that the fixed points are A and D. So just below the space diagram, keeping some space to draw the velocity diagram, you indicate the fixed point A comma D. And also again I'm reminding you, in the velocity diagram we indicate the points with small letter alphabets. Now to indicate the velocity of B relative to A, we have found out the magnitude and direction. What you do is, from point A comma D, you have to draw a line parallel to this line. Okay, from point A comma D, you draw a line parallel to this line, and the direction should be towards the right. Okay, so that means from A comma D, you have to draw a line parallel, okay, to this line. You have to draw downwards from A comma D. Okay, and the length of this line will be the magnitude. Okay, so the magnitude of velocity, we have got it as 9 point something meter per second. So maybe it is difficult for you to represent it in the paper. So what you can do is you can scale it down. Okay, so 9.9 meter per second you can divide by 2. So it will come around 4.5 centimeters. You can indicate that length, or you can draw that length. Okay, so that means you need to divide the magnitude by a scale factor of 2. So I have drawn it like this. This is what you will get. The end point of this vector will be point B, and when you mark this arrow in this way, that is from A comma D to B, it indicates velocity of B relative to A. Okay, so the sign convention, or the way in which you designate velocity, I have already explained in the previous video. Okay, so when we indicate the arrow in this way, then it actually indicates the velocity relative to the head relative to tail. Okay, so we have represented the velocity of point B relative to A. After this, we have to go to the next link. The next links are the connecting rod BC and the output link CD. And we have also seen that link BC has a general planar motion, and link CD, or the output link, has a rotational motion. So first, since we can it is easier for us to analyze or find the velocity of that output link CD because it is having pure rotational motion. We will consider link CD. Okay. Now regarding the motion of link CD, we don't know the magnitude of velocity of C relative to D, or we don't know the direction, right? But we know one thing. What is that? We know that the line of action of velocity of C relative to D will be perpendicular to CD. Okay? That means what you do is from C you draw a line perpendicular to CD. You can extend that line on either side of CD. Okay? Okay? Now what you do is, so again I am repeating, I am going to draw a line from C perpendicular to CD. Okay? Now what you do is, we have this velocity diagram. We have point D here. From point D or AD, you draw a line parallel to this line. Okay? From point AD, you draw a line parallel to this line, what you have drawn. Okay? So here. You can extend that line on either side of point AD. Understood? You don't have to take any length. You just have to extend. So that is what I have done here. Okay. Here. So first I have drawn a line perpendicular to link CD, and from AD in the velocity diagram I have drawn a line parallel to this line. Okay, and again I am going to remind you, this line is nothing but the line of action of velocity of C relative to D. Line of action. Okay, because we don't know the exact direction, but we know that the direction of velocity will be along this line. That is why we call it as line of action. So now we have considered first the driving link AB and the driven link or the output link CD. Now we will consider the connecting link or the connecting link BC. Okay, and we know that the connecting link having a general planar motion, which is a combination of rotational and translatory motion. But for the purpose of drawing the relative velocity diagram, we assume that link BC rotates either about B or about C. Okay, whichever point we can assume, it doesn't matter. Okay, so regarding the motion of BC, we don't know anything. Our case is similar to that of CD. The case of BC is similar to that of CD. We don't know much information regarding the magnitude of velocity or direction of velocity. But here also we know that the line of action of velocity will be perpendicular to BC. Okay, so what you do is either from B or from C, from either point you can take. Okay, you draw a line perpendicular to link BC. Okay, so here I'm going to draw the line from point B. You draw a line perpendicular to BC. Okay, and now in the velocity diagram, this is point B here. Okay, from point B you draw a line parallel to this line. Okay, so that these two lines will meet. Okay, and this point is C, small c. Okay, so that is what I have drawn. First I have drawn the line of action of velocity of C relative to B or B relative to C, that is this line, and then from point B I have drawn a line parallel to this line of action. Okay, and that parallel line will meet the previous parallel line at C. Okay, so what you get now is the velocity diagram for this 4-bar mechanism. Also, you please note the way in which I have indicated the vectors. Okay, you can, the arrows are not, the direction of arrows are not fixed. Okay, so you can indicate in the opposite way also, but as I have told you, when you indicate it in the opposite way, then you must designate in that particular way. Okay, always the designation will be from head to tail. Okay, so that you please note. Now using the velocity diagram that we have drawn, we will try to solve the question that is asked. In the question, we have been asked to find the angular velocity of the connecting link BC. Regarding link BC, we know that the connecting rod will have a general planar motion, but as per our assumption, we assume that the connecting rod is rotating, has a rotational motion either about B or about C. So if we assume that the connecting rod is having a rotational motion about B, then we can find the equation, find the linear velocity of C relative to B equal to R. Velocity of C relative to B will be equal to R into omega, right? Here what is R? R is nothing but BC or CB, length of link CB into omega CB or BC, both are the same. Okay, now from this equation, which are the known values? Anyway, omega CB is what you need to find, that is the angular velocity of link CB. The length of the link CB is already given. The length is given in millimeters, so you need to convert to meters. What about the magnitude of velocity of C relative to B? That you can find from the velocity diagram. Okay, so the magnitude of velocity of C relative to B will be equal to length of CB, length of line CB in the velocity vector. So you take the measurement of line CB in the velocity diagram and then you substitute in this equation, you can find angular velocity of CB. But one important thing that you must remember is that when we drew the velocity diagram, we had scaled down. Okay, we had divided by a scale factor of 2. So what you do is, when you take the measurement of CB, when you take the value of CB, you need to multiply it by 2. Okay, then only you will get the value for velocity of C relative to B. Okay, so you must remember that the measurement that you take from the velocity diagram must be multiplied with the scale factor 2. Okay, so that is what I have done here. I have got the velocity value as 6.4, and finally I am getting the angular velocity as 17.78 radians per second. You please check the answer. Depending upon the accuracy in which you have drawn the velocity diagram and the space diagram, you will get a slight variation in the answer, but the variation should not be too much. Okay, ideally the way the pencil sharpness, everything, and the accuracy of your instruments, everything will affect your accuracy. Okay, so please check, you please draw your figure with sharp pencils. Okay, thank you.